Okay, so before we look at the problem with these kind of like conservation of momentum collisions, we're going to look at one example. I know we've seen like a million of these pulley problems. Well, I hope a million maybe, or it feels like it maybe, right? So we're kind of familiar with, these rotating pulleys. We've seen a lot of different examples. So we also can model these as conservation of energy. So we're going to get to a midterm problem that's going to deal with two different things. It's going to have conservation of angular momentum and then also use conservation of energy. So we're going to introduce both of them and we're going to look at conservation of energy using rotational kinetic energy. And then we're going to try to put all the pieces together with our later problems. Okay, so all right. Two different things in the system, right? We have this mass of the stone. So we can just kind of model this as a point mass. This guy's not rotating. And then we have the mass of this pulley. This guy is rotating, right? And they're connected by this rope. Okay, so uniform solid disk for this pulley. So we know that the mass moment of inertia for a pulley is going to be, so pulley is going to be equal to 1/2 mr squared. We've used this guy a lot before. Okay, now what else does our problem give us here? So we have the mass of the pulley. So we have the mass of the pulley, MP, is equal to 2.5 kilograms, right? We know that the radius of the pulley, I don't like it when they give you different units. I just think it's like very annoying for a problem when they do that. So this would be 0.200 meters. So centimeters to meters. I don't know why they just don't give you all the same units. I think it's kind of a waste. Okay, I guess conversion is a good thing to practice, but anyways. Okay, then we have a stone. So we have the mass of the stone, and that's going to be equal to 1.5 kilograms. Okay, then the light wire. So we're not modeling any of the mass of that wire. Okay, we're just going to treat that as kind of like a separate thing. And then, so we know it's also wrapped around the rim of this pulley and it's sort of unraveling as this stone is moving down. Okay, so I think that's everything that we're given to start with here. Okay, so we just know the two masses and then the radius of the pulley. And then we know that we have this I value for the pulley. Okay, so we are going to look at this in terms of conservation of energy. Okay. Oh, we do also know one other thing. So let's see. How far must the stone fall? Okay. Okay. So for part one, we're asked to find how far the stone needs to fall to have a kinetic energy of 0.4 or 4.5 joules. Okay. So to figure out how far the stone falls, so let's say the stone starts here and then ends up where it is there. So we'll just call this like these, so we've got these 2 points here. So this would be some negative delta, like some negative h. We'll call it a negative h for this problem. Okay, so, and then for that negative h, we want a kinetic energy for the pulley. That's going to be equal to 4.5 joules. Okay, so let's start with part A and see what we need to do for that. Okay, so we want the kinetic energy of the pulley to equal 4.5 joules for the first part of this problem. So energy of the pulley, which would be equal to, let's see. So our general expression for kinetic energy for this one is going to be 1/2 IP W squared. So 1/2 the right I of the pulley times W of the pulley squared, but we don't know that, right? So we need to figure out a couple of different things. So we do know the I of the pulley. We can go ahead and just kind of like plug in what we have. So let's just say that we know this, and I'm going to write out just IP is equal to the solution for that would be 1.05. This is just a matter of plugging numbers into a calculator. Kilogram meters squared. Okay, so once we're given everything that we need to find that one, so we just are plugging it into our calculator. Okay, so we have that guy. So we want the, let's see, far must the stone fall. So let's figure out the kinetic or the angular velocity here. So WP, so we want this to, so if we're rearranging this, right? and we want the kinetic energy to equal this guy, we're going to end up with, if we just rearrange this, we'll have W is equal to the square root of the 2 KEP over IP that we know. So we want it to be equal to, so we're going to plug in KEP equals this 4.5 joules, right? So we're going to figure out the angular velocity. Okay, so we're just finding an intermediate step here so we can use it for conservation of energy, because we need a few more pieces, right, to figure out the how far the stone falls. Okay, so our W in this case, if we plug this in, is going to be equal to 13.4 radians per second. Okay, so we solve for this intermediate step. Okay, because we're going to need to be able to sum our kinetic energies, right? Okay, so to figure out how far the pulley must fall, we're basically, I mean, we're like reverse solving for this problem, right? So we're going to set in a, we're going to set our kinetic energy, and then we're actually just going to solve for height. So we're going to get our intermediate steps. Okay, so we have this W here. Okay, so this would be our WF, I believe here. Okay, so what we need to do, so we're going to model our system. So for conservation of energy for our system, what we would have is we'd have K1 plus U1. So the initial energy plus the kinetic energy plus our potential energy is going to be equal to K2 plus U2, right? So U is equal to potential energy. We see it written in different forms, right? But this means the same thing. And then K would be equal to our kinetic energy, okay? So just sort of different notations. I do want you guys to kind of be comfortable with kind of a mix of them. I forget what your book uses. I think it's U and K, so I think this is hopefully consistent. Okay, so what's the initial everything here? So initially everything's at rest. So both of these would be 0 initially, right? 0 and 0. What about our final for both of these? Well, for the final state of our system, we would have a K2 value, right? So we would have things that were moving. So our final kinetic energy, we have two things that are moving, right? This is going to be spinning, right? This is going to be spinning, and this object is going to have a linear velocity. So when you're asking yourself, like, how do I find those energies? Where are they? Ask yourself, like, what in my system has a velocity? Okay. And then what in my system has a height change? Okay. For potential. So I think sometimes the kinetic ones are confusing. So what has a velocity at the end? So this has an angular velocity and this has a linear velocity. So we know that we have rotational kinetic energy and we have a linear kinetic energy. So our K2 is going to be equal to, we have this 1/2 mv squared, right? For our falling stone, okay? So our falling stone, I'll put that guy in there. So we solve for our Ke for the pulley. So let's say like Ke for our stone, and then K2, we know that it's going to be equal to the Ke pulley plus Kes, okay? So this is the net that we're trying to solve for here, right? We're trying to solve for the state where we have this final kinetic energy plus a final potential energy, okay? So what is the Ke for our stone? Well, Kes would be equal to 1/2 mv squared, so m of the stone, right? And then v is equal to v, or v tangent, right? V tangent squared, basically. So there's a relationship between both of these guys. Are we given? Yeah, we do know this. Okay, so vt squared. Okay, so when we have rolling motion without slipping, which we do when we have a pulley that's unraveling, we know that we have a relationship between the angular velocity, right, and the tangential velocity. So there's a relationship between the angular velocity, so how this is spinning, and how this string is coming off of the pulley, right? So I think I've drawn this before for acceleration, but if I have a circle, right, and I have this angular velocity w, I'm going to have this tangential velocity, right, going off in both directions, and vt is going to be equal to rw, okay? So we can find our tangent velocity for this problem by using the RW relationship, right? Because we have the radius of the pulley and we have the angular velocity of the pulley. So we're going to use that to solve for VT. So we know that VT is equal to, what was the radius of the pulley? 0.2 meters, right? 0.2 meters. And then we found 13.4 radians per second for this WF, right? So times 13.4, and then that's going to give us our VT. Okay, and then we have the mass of the stone. That part is given to us. So we have the mass of the stone and we can just plug that in. And then we're going to get our KES is going to be equal to final value of, well, actually I'll write the VT out here first. So, sorry. So we know this relationship is true. Our VT is equal to 2.68 meters per second. And then our KES here is equal to 5.39 joules. Okay, so we have this guy, right? KES. Okay, so we know this KES, right? And then we know this KEP. We were actually just given, it was given to us by the problem, right? They were like, I want this initial kinetic energy for the pulley, right? I want this value. And then with that pulley, with that pulley kinetic energy, we were able to find W, and that gave us the ability to find the kinetic energy for that stone. Okay, so now that we have both of those, we're going to plug in, right, our value for the kinetic energy for the pulley and then the kinetic energy for the stone, right? So we're going to plug in this guy right here and this guy. Okay, and then we have our K2. And then once we have our K2, we're looking at the rest of our general system, right? I'll go ahead and add a page. Okay, so we have our K2. So we were using this, right? So we know that we're using conservation of energy. So we have the initial energy of the system is 0 for everything. And then we have our final kinetic energy. We have the spinning pulley, the falling mass, and then we have one other thing. We have our U2 value, right? So we have this K2 that we found. So that's great. We can take that K2 value and then we can get that guy in there. And now we need our U2 value, right? So U2 is going to be equal to mg, right? The potential energy change, mg times the negative h value. Okay, that's great, right? So we are trying to solve for how far in h we're going to fall with that kinetic energy, right? So we have 0, if I just simplify this side, right, is going to be equal to KEP plus KES minus MGH, right? So just plugging that guy in over there. So we plugged in this one for U2, right? Because that's our change in potential energy as this rock falls, because we're thinking at the end, so what has velocity and what's changed in height to find our pieces. Okay, so then we set MGH is equal to KEP plus KES, and then we are just going to say H is equal to KEP plus KES divided by MG. All values that we have. And this MGH, the change for MG is actually this mass on the bottom. Mass on the bottom here is going to be the mass of the stone, right? Because that's the only thing that's changed in height. So if something's changing in height, the mass that's changed in height is the one that you're using for that system. Okay, and so the mass of the stone that you would plug in there would be, I forget what they gave you, 1.5 kilograms. And we know gravity. So the net change in height for the system, the final answer here would be 0.673 meters. Okay. All right, so that's our final answer for part A. Okay, so then part B is what percentage of the total kinetic energy does the pulley have? So for part B, we're just looking at kinetic energy. So for the pulley, it would be KE pulley, right, divided by K2, because that was our total kinetic energy that we found, right? This is our total kinetic energy. The other piece is potential energy, okay? So we just want to know how much of the kinetic energy the pulley has, not how much of like the total system energy, just the kinetic, okay? So what was the pulley? The pulley was, so it's, yeah. So we have 4.50 joules, and then the total for K2 is 9.89 joules. So the kinetic energy that the pulley has in the system is equal to about 45.5%. So that one's just the ratio that they want to ask you for. Okay. So to summarize what we did here, so we had a system that was rotating and a little mass that was falling, and we had a change in height. So we were asked to find how far the stone needed to fall so that the pulley had a certain kinetic energy. So we took the kinetic energy for that pulley. We found the angular velocity. We know that our system energy going in was equal to our system energy going out. We had energy conserved in this system. We didn't, so we just set K1 plus U1 equal to K2 plus U2, no non-conservative forces here. Then we used the angular acceleration to find the velocity that the stone was falling with, because we used the relationship of this no slip condition where our VT coming off the circle is equal to RW. Okay, solved for VT, found the kinetic energy of the stone. So then when we had both of these, our total kinetic energy at the end, this K2, is equal to the sum of both of them, right? And then our potential energy at the end is equal to this mass times gravity times the change in height for the stone as it fell, okay? So everything at the end that had velocity went into K2. Everything at the end that had a change in height went into U2, okay? Because we modeled our 0 point as like here, and then our final point here, just looking at the change. Okay, so yeah, so then we plugged everything in, we solved, we used our mass of the stone for the change in height because that's what changed in height, and then we found the height. Then at the end, we found our ratio of the pulley to the total kinetic energy, because that's all it asked us. It could also ask us like how much energy does the pulley have in relation to the full system, right? But in this case, they just asked us for the ratio of kinetic energy, and that was 45.5%.